We have Miroslav Jeras from Pebble Beach Systems, and he's going to be talking about NMOS 07, which is very important because we not only need to have video and audio going over our IP networks, but we need a way for replacing all of those contact closures and tally lights and all those other things. So Miroslav is going to talk about that and obviously a lot more because it's a very important and intriguing topic. So thank you very much, and over to you.
Hello everyone, welcome to the IP Showcase Theater. I'm Miroslav Jeras from Pebble Beach Systems, and we are going to have a look at NMOS ISO 7 protocol. So let's start with some general information. So this is one of the new additions to the NMOS set of interface specification within AMWA. So the full name is AMWA ISO 7 NMOS Event and Tally. It's a formal definition of the protocol would be that it's a protocol that allows the source to publish its state and communicate its state changes to subscribed receivers. We'll see later what it actually means in the real life. The protocol, as the rest of NMOS, is published on GitHub, both as a repository of documents and schemas, and as nicely rendered pages. I'm trying to, let's say, give you a story and what was actually the process, how we got to this standard, the thought process behind it. So what we had previously before the IP world were the traditional GPIs. Those are basically electrical signals going up and down, carried over cables, and that's not something that you can use in the modern IP environments. I mean, if you have an IP facility on-prem, maybe you could run the wires, but it wouldn't make much sense, to be honest. If you go to virtualized platforms, especially public cloud, well, you won't be running cables in AWS, for sure. So we needed something to replace that functionality. So how do those cables translate into the modern world? We have on-off electrical signals in GPI. The matching is a Boolean data type carrying true or false values, carried over the network. No cables anymore, at least not that kind of cables. And the messages are formatted in a modern, web-friendly way, let's say, humanly readable and machine readable. So the JSON format was picked as the message format for the messages. Now, one of the first questions that people ask is, when you had a cable, a wire, then when the voltage would appear on one end, it would almost immediately appear on the other end. But with networks, we know that there are delays in transport, and also those delays are sometimes variable. So what about that? So one of the first principles of ISO 7 was to add a timing section within the JSON message, and those timestamps are actually PTP timestamps. So PTP, as you know, is at the core of 2110 and all the IP networking, and has a very, very high precision. Actually, even much higher than what is needed for this. But it does allow absolute frame accuracy or even audio sample accuracy, as this resolution is nanoseconds. And that timing section contains actually a number of different timestamps. So one of them would be the creation timestamp. So if a message is created, it carries this timestamp carries the time when it was created. If that message then triggers another action, the original timestamp can be carried also in the message and propagated throughout the chain of events. And also, probably the most important one for frame accuracy is the activation timestamp, which tells you when the action should actually happen. So if you want to trigger a number of devices at the same time, you would send the activation timestamp so they have a pre-roll time for all of them to actually start performing an action at that very time. Given that it is the PTP layer is fundamental for 2110, it would also allow total accuracy even if there is a delay, let's say, in video distribution, and if ISO 7 message comes with a timestamp, the receiving device could actually wait for that exact time frame to come on the input to start the action, not necessarily at that time, but it can actually match it with the video flow. But then, this was just GPI replacement, but we have now defined a JSON message that could be extended. Why would we just send Boolean values? So the next step was adding strings and numbers, which are common, well, default types in JSON. But if you would just receive a number, let's say 50, what does 50 mean? It could mean various things. So there is another layer in ISO 7 which adds type definition on top of those communication channels. So a sender would say that it, let's say, supports the degrees of Celsius. So when the receiving device receives that 50, it knows that it is 50 degrees of Celsius, not Fahrenheit or 50 megabits. In addition to that, you can also specify range. So let's say if the receiving device wants to put a nice GUI with a thermometer, it will know the range from -20 to 100. Of course, it's not just for temperature. You could have that for attenuation level, or you can use it for data rates or any other numeric value or measurement that you might want to carry across the network. Another thing that is accomplished using value lists is sending off enumerations. So, you can have just a string sender, which can carry anything, which is useful in some cases. But sometimes you want to say that only 5 values are allowed, and then maybe provide some additional metadata on that. So enumerations are available on top of all the basic data types. So even for true false, you can say, okay, true means on, off means off for this Boolean sender. Another Boolean sender might have different association. Also, probably the most common type of enumeration would be 0, 1, 2, 3, and then the type definition would attach meaningful values to those 1, 0, 2, 3 values. So how does it look like in JSON? So this is a sample message. It doesn't have all the possible fields, but has, let's say, a decent set of it. So there is an identity section which says which source does it belong to and which flow does it belong to. That is particularly useful when debugging some issues that you might encounter. The next element is the event type. And based on the event type, the control system will know how to match sources and receivers to make sure that it doesn't connect a number sender to a Boolean receiver, because that won't work. So this is declared also in the message, but also in the registration in ISO 4 of those senders. This timing section in this example is a basic timing section, just creating the mandatory creation timestamp. But as I said, there could be other pieces of information in there to help you be more accurate. This element, payload, is the key element, as that one carries the value. So for now, it could be Boolean, string, and number, but in the future, it will be expanded to other things. This is a sample type description. This is a bit more complicated one, which restricts the string type to 4 values. And each value also carries, let's say, a label. So if the receiving device doesn't want to say just unknown OK warn, and this could be also numbers, 1, 2, 3, 4. So instead of just sending the value, which is the value that is transmitted in the message, it can actually look up the type definition and say, okay, I should put device state is unknown on the user interface. Or if somebody, let's say, double clicks, it would have a description available there to display. Of course, it depends to the implementation what is done with those values, but they are in the specifications, so the devices can use them. So we have defined the message format, but what about the transports? So what is our cable from the early GPIs, the physical GPIs? We have two protocols to choose from. So the first one is MQTT. MQTT is a broker-based protocol which is very common in Internet of Things. It is based on a broker to which all the devices subscribe to. They connect to the broker, and the receiving devices subscribe to topics. So in case of ISO 7, topics are the IDs of the NMOS components, senders or sources. MQTT allows for one-to-many connections because the sender connects to the broker, says I'm publishing on this topic, and then any number of receivers can connect and listen to that topic. The main use case for this is highly scalable and highly reliable environments where you might have many machines in the system and you want to reduce the number of connections that are going on over the network. So you don't end up with one machine being connected to 100 other machines by opening 100 sockets. On the other hand, we also have WebSockets as one of the communication protocol. So again, this is a well-known protocol used widely on the web, but it is also an existing NMOS protocol, as this is the mechanism how the ISO 4 registry communicates with its subscribers. Now, unlike MQTT, WebSockets is a brokerless protocol. It also means that it is one-to-one. So if you want to connect 5 machines, you would have 5 WebSockets listening to the source machine. But it covers a different set of use cases. For example, if you have MQTT, you have to administer probably a redundant broker. So you have to install it, administer it. You would have to have probably a couple of VMs that would be running that. So that is a little added layer of complexity, which is well worth if you are talking about a big facility. But in a smaller system, it could be a bit of a burden to administer. But also, if you know that in your facility you will be mostly connecting devices one-to-one anyway, and you won't have many one-to-many connections, WebSockets might be the optimal choice because they are direct. So there is no broker there. Because if you use MQTT, there would be one connection to the broker, there would be the broker queue, and there would be the connection back to the receiver. In this case, this is one-on-one, so it will probably be at least twice as fast as MQTT, which could be critical in some use cases. There was a very long discussion as to which one should be mandatory. In the end, the decision was made to make both of them mandatory for the implementers, as we don't know in which use case ISO 7 would be deployed. As bigger systems would probably opt for MQTT, smaller for WebSockets, but also big systems where certain connections have some critical speed requirements could use even a hybrid model using both protocols. An added benefit of ISO 7 is that it is based on top of ISO 4 So it has the same sources, flows, senders, and receivers as the RTP transport has, and they all get registered in the NMOS registry. Also, ISO 5 connection management sits on top of that, and all the connections are basically managed with ISO 5. The only thing is that two new protocols were introduced. So for ISO 7, new versions of ISO 4 and 5 are required. So version 1.3 of ISO 4 and 1.1 for ISO 5. But there is a number of registries already that support those protocols. When you have your RTP streams, you might want to add some metadata on top of them. Let's say channel name, countdown to the next event. And then you can group that metadata with the video and audio using the same BCP 002-01 natural grouping specification, which identifies those metadata flows as being a part of the same group and defines their roles. So just summarize the use cases. So we started with the GPI replacement. The next use case is basically modeling physical components or virtual components of control panels. You could have button panels, you could have like vision mixers with sliders, knobs, various other devices, or on the other hand, LED lights, stuff like that, which can all be modeled using ISO 7, and you can establish connections between those components and receivers who would receive those values. Sensor readings are another use case. We talked about, let's say, temperature before, but that could be any other sensor. Annotation of the media streams. So what I mentioned when talking about grouping, you put the channel name as an ISO 7 feed together with your RTP stream. So when it comes to the multiviewer knows what is your channel name. So it will automatically add the label underneath it. It won't require some control system magic to do that. Also metadata transfer, counter, stuff like that. But also another excellent thing about this is that also allows custom communications between devices to be implemented on top of that. As you have seen in the message format, we have the payload field, which is basically a JSON structure. So you can put any even proprietary data in that and still use all the other benefits. ISO 5 connection management, grouping, and all that, and you have a standard protocol to transfer your data, even if you are working on a project where you have to connect to specific devices. And actually, from our experience at Pebble, as we are working on a project that is going to be live this year, we call it a Swiss Army knife for system integration. As when we were looking at the requirements for the project, there were a number of requirements where the customer suggested that an open standard should be used, but while we had to communicate some very proprietary data between our system and the control system or back, or send some telemetry around the system. And ISO 7 was like a universal answer for everything where there was not a already defined standard. Now let's have a look at where we are in the development of ISO 7. So the project started early last year. It was started by Suitcase TV, and a number of companies joined the project. And in July 2018, we had the first workshop in Wuppertal in Germany, where a couple of companies were testing the initial specification. At IBC 2018, there were 2 or 3 demonstrations already on vendors' booths. And in November 2018, the specification was approved by AMWA board. In the workshop in Newbury in January, there were more companies involved, and more implementations were there. There were registries that supported ISO 7. There were control systems that were able to connect ISO 7 senders and receivers, and there were devices implementing stuff on top of that. And at this NAB, we have a demo at that wall where we are showing probably the first system, although a demo system, that is doing something meaningful using ISO 7. So the components that we have in that demo are a button panel, a cloud system, a cloud automation system, a multi-viewer, control system. And the data types that are being transferred are Boolean button presses, where the panel is modeled. There are numbers carrying either enumerations of the layout to be used, number of the layout to be used, or the color for the buttons. And also we have strings being transferred, which carry regular text like names of the channel, time code, or even an image. Although that is a bit out of the phase 1 spec, but was an experimental effort to see how that can be done. So what next? Right now we have the data format, we have the transport protocols, but we don't have anything defined as to what is expected from devices. So what a button panel should do, for example. So that is one of the things to be specified. What does let's say a very simple button panel have to do? Probably just send true and false, depending on the key press. A more advanced button panel could receive the labels and the color, and some even more advanced panels would be allowed also to expose their proprietary formats. The other thing that will probably be discussed in the next stage is how we define complex objects. As right now we are just using elementary types. So how do we define and restrict the payload that goes into there? Also, do we do incremental updates, for example, for some big objects? Adding more use cases. One of the proposals is to carry telemetry data, as we have a placeholder where we could put a structure describing, let's say, an IP port. So the plan is to work on that after NAB, and then have some of those things at least tested at the next AMW workshop. And there will also be first projects delivered in summer of 2019. At ABC 2019, we hope to present the next stage and the developments in the next stage. That's it. Thank you all. Not sure if you have any questions.
In consideration of the button press use,
Yes?
consider multiple presses. If, for instance, make sure when you look at this that you have to have a case where there might be a shift button that's held down to do other things, and have whether you're going to force that logic back on the panel button panel manufacturer.
Well, it could happen. Well, there I could see two scenarios. One would be that the button panel would have twice the number of senders than it has buttons, probably -1 if this is used for shift, and then it has actually, if you press shift, you expose different buttons. But you can also transfer that functionality to the control system, and that would be the preferred way. So don't put that logic into the button panel, but in the control system. Actually, I would like to invite you all to the demo after this talk so we can have a look, and I will show you probably something also that might answer your question, as we have something similar going on there.
All right, Miroslav, thank you very much.
Thank you all for your patience.